Hello again. Welcome to, woohoo, how exciting, the last chapter of our pre-calculus course. This one, after exponentials, this one is devoted to the inverse of an exponential, something we will call logarithm. Yes. So let's talk about logarithms, the big bad beast from high school, the one topic that everybody hates. It's really not that bad, really. So, what is a logarithm? What a word. What a word. What a word. What a word. Well, it's a mathematical invention that actually goes back, I think, 300 years ago when people actually tried to solve equations. Equations that required very, very fancy calculations back in the days. But for us, it's going to mean more the connection to an exponential function. So let me just explain. What is a logarithm? Well, what is the solution? What is the solution to the following equation? 2 to the power of x is equal to 8? Question mark. All right, so I have an exponential function here, yes. It's an exponential because the power of 2 is x, as we all know. And if I want to solve this, I have seen in previous videos that it was going to be a lot easier if I'm successful writing 8 as a base of 2. So that's my job here. Try to write 8 as a base of 2. 2 to the what shall give me 8? 2 to the what power? 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 3 is 8. So because the bases are the same, I can conclude that the exponents as well must be the same, right? Well, when you solve an equation like that, the answer you get is actually, believe it or not, what we call a logarithm. This is a log. This is a logarithm. More precisely, I can't spell. More precisely, we say that the number 3 that we have, the answer to this equation, the number 3, is actually equal to the log of the right-hand side, 8, with a base of 2. So the answer here, which is just basically what exponent should I give to 2 so that I get 8, this answer can also be written in that way. This answer 3 is also log of 8 base 2. By the way, this is red. This is red. Log of 8 base 2. All right, so that's an interesting concept, that really the answer to an exponential equation turns out to be a log. From this, we can actually extrapolate the connection that exists between logs and exponential in the following way. All right. So 2 to the power of 3 equals to 8 corresponds, in the language of logs, corresponds to, what did we say this was equal to? That number 3 was actually equal to the log of 8 base 2. Log of 8 base 2. Like this, right? Those two expressions are talking about the exact same reality. So it will be convenient to have some sort of a transformation formula to go from one to the other. Because after all, as you can see, a log is nothing else than an exponential written differently. Huh? So, in general, what can we say? In general, what can we say? We can say the following. A to the y equals x. Suppose I have an equation like this, a to the y equals x, which makes me think of 2 to the 3 equals 8, right? So 2 to the 3 equals 8 sort of expression in general. This will be the same expression as what? As log to the base of a of x equals 2y. Yeah? Let's compare what I have here with what I have there. 2 to the 3 equals 8. So if I compare 2 to the 3 equals 8 with a to the y equals x, I have that a is 2, y is 3, and x is 8. Huh? A is 2, y is 3, x is 8. You can see that the connection here is really a one-to-one connection. Now, I have a little bit of a mnemonic to propose to you to remember this most important and fundamental connection. I basically, this is how I remember it. I take the base, and then I raise it to the power of what's on the other side. So I take the base a, raise it to the y, and I make that equal to what's inside the log, which is x. So for me, this is a to the y equals x. Kind of a loop like this, okay? So let's keep that in mind. Let's keep that in mind. Let's actually box this formula. So a to the y equals x, same as log base a of x equals y. So this is how one transforms an exponential into a log, or vice versa, a log into an exponential. We're going to be concerned more like going from right to left in order to evaluate different things, right? Okay, so that is the fundamental log connection. Let's see if we can practice this on some examples. All right. So, all of my examples in this video, they will all be 2.5 stars. So I will not relabel. I have 5 or 6 examples, I believe. I will not relabel all of them. They're all of the same level. They're all 2.5 stars. So example 1. Evaluate. Oh, I did prepare a few examples for you guys. So what do I have here? Evaluate log of 16, and the base is 2. Now the first thing that I want to say here is that our calculator is going to be useless for this, at least for a while. The calculator doesn't have a button for log base 2. We're going to talk about how the calculator can help us evaluate some of the logs in a minute. But for now, immediately speaking, if I were to use my calculator and only my calculator to do this, I would not be able to. The calculator doesn't have a button for log base 2. It does have logs though. It's going to help us with some logs, but log base 2, the calculator is useless. So how do we solve this? I am going to say what any good algebraist would say. You don't know what something is, call it a variable. Let log base 2 of 16, let's call this x, y, z, whatever. I think we called it y previously. So let's stick to our guns. Suppose that I call what I don't know, I call it y. Let us transform this log into an exponential the way we know how. What is the way we know how? This way. Take the base, raise it to the power of the other side, make it equal to what is inside the log. All right, so 2 to the y, so this is the same as 2 to the y, so base to the right-hand side, egal the inside of the log. Now, I think I know how to solve this. It's pretty easy, but it requires us to write 16 as a base of 2. So 2 to the what power is 16. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16. Yes. So, again, we have the same base, so the exponents must be the same. So it seems like y equals 4, but y was precisely what we called this log. So log base 2 of 16, which we put equal to y. We have now identified the y. Y is 4. And you've identified a log. Check. How do I check that this answer is correct? Well, 2 to the 4 equals 16. Is that a true thing? Of course it is. Check mark. 2 to the 4 is 2 times 2 times 2 times 2 is 16. So we've successfully evaluated log of 16 base 2. The answer is 4. Good? All right, let's take a look at another example of the same caliber. Okay, what do we have here? Well, first of all, we have example 2. Okay, let's evaluate log base 10 this time of 1,000. What would that be? Okay, now I know some of you remember some of the things from high school. You may remember that log base 10 is in fact a button on our calculator. It's the LOG button on the calculator. So if I just press log of 1,000, I'm going to get the answer right away. You might want to do that on your calculator right now. Take out your TI-30 and put in log of 1,000. You should get your answer. What did you get? You got what? 3? Very good. Let's verify that this is true by doing our little change the log to an exponential approach. So let log base 10 of 1,000. We don't know what that is. We know, but we don't know. Let's make it equal to y. So this is the same as what? Once again, our standard little strategy, take the base, raise that base to the power of the right-hand side, which is y. Make that equal to what's inside the log. 10 to the y equal 1,000. Yep. So we know that we will be successful solving this if and only if we are successful writing 1,000 as a power of 10. Well, there are 3 zeros. 10 to the 3, as a matter of fact. 10 times 10 is 100, times 10 is 1,000. Same base, 10, so the exponents must be the same. But once again, what is y? Y was what we call the original dude. So, conclusion, the original dude, or dudette, don't know. The original dude is equal to 3. Quick check. Quick check. Well, how do I check? Again, same story. Base to the power right-hand side equals inside of the log. 10 to the power of 3 equal 1,000. Of course, this is a true statement. Check. Yes? So, it's more or less the repetitive thing that we're going to do there, or just going to add a couple of tweaks here and there, but there it is. That's what it is. That's how one evaluates basic logs. Now before we go on, let me make a quick comeback on that log base 10, which is on the calculator. Okay. Now, remark. I have two little remarks to make. The first one, log of something that actually is the same as log base 10, right? So when you see log without a base, it is assumed that the base is 10. Also, you will meet this other guy, ln. Some of you remember that perhaps from high school. ln, sometimes referred to as the Neperian log, sometimes referred to as the natural log. This is just another log, but with a very, very, very special base. What is the base of the ln? Do you remember? Well, it's the same special number that we spoke of when we talked about it. Special numbers and exponentials. This is the number e. Yes, so ln, when you see ln, I'd like you to think that it's a log to the base e, where e is the same number as before. That is 2.7181. You can get the precise value if on your calculator you press e to the 1. If you use your calculator and you actually ask a calculator to calculate for you e to the power 1, it'll spit out this value with a lot more decimals than what I put here. All right, so terminology in the log. Well, let's use this in our next example 3. Evaluate the ln of the root of e. That looks intimidating, doesn't it? ln and e and roots and things. But let's not be intimidated by that. Basically, let's tackle this from our good old analysis base. So, I don't know what that is. I am going to call it a variable. Call it x, call it y, call it w, call it what you want. So, remember that ln, as we just saw, remember that ln is log to the base e. So, this is log to the base e. Of what? Of root e. Now I'm going to change my log to an exponential the way I taught you how. So e to the power of the right hand side equals to what is inside the log. So this expression turns into what? E to the right hand side equals to the inside of the log, root e. That is, e to the y equals what is the same thing as the root of e? E to the what power? What's the square root the same as? If you answered e to the 1/2, you are correct. And once again, the bases are the same, so the exponents must follow. So here, it follows that y is 1/2. But, again, y was what we called the original expression. So, the ln of the root of e, that is actually equal to y, which is now 1/2. And this is how we would evaluate this. Yes? Of course, there's a button on the calculator that actually is called ln. So if I actually ask the calculator ln of open bracket square root of e, close bracket, it will spit out 1/2 or 0.5, guaranteed. So just to summarize this calculator connection here, the calculator has two keys on its board. One for log, which is going to be log base 10, yes? And one for ln, which is going to be log base e. If we are asking the calculator about log base 4, log base 20, log base 7, it doesn't have a button directly for that. All right. Let us see if we can try something else here of the same nature. All right. So what are we down? Example 4 now? Example 4. We're still in the realm of 2.5 stars here. So evaluate. That's a bad E. That's a beta E. So evaluate this expression log base A of A. Basically what I'd like to get out of this is a formula or an expression or something that I can apply when I see that the inside of the log is the same as the base. So what is that equal to? I don't really know, so I'm going to do what I usually do. I am going to let it equal to a variable. And then I'm going to use my change the log to an exponential strategy. A to the y is equal to the inside of the log. So a to the y equals to the inside of the log. Notice that the inside of the log is actually a, and a is 1. So right away my bases are the same, so the exponents must be the same. So y must be 1. But y was the original thing, so here's what we can actually call an identity for logs. Log base a of a is actually 1. To this, I am going to put a restriction, which will become clear in the next video when we talk about the graph and the function ln x or log x and its domain. But for now, I'm asking you to take this for face value. This actually holds true whenever a is a positive number. Notice that it's not greater than or equal to 0. It's only strictly greater than 0. So that's kind of an identity. If you want, we can box this. When we see this, we will know right away, no calculations needed, we will know right away that this is equal to 1. So I can do a very quick example 5 here. Example 5, what is log base 4 of 4? Well, the base and the inside of the log are the same. So answer 1. Answer log base 4 of 4 is 1 because my identity here tells me so. All right. Okay, I think we're starting to get the drift of this. Maybe one last example. And that'll be enough for the day. Well, the day. The video, that is. About the day, we don't know. All right. So this would be what, example 6, I guess. Evaluate. What should we have here? Evaluate minus log base 5 of, say, 125. How would we do that? Again, the calculator is useless because it's neither a base 10 nor a base E. So it's not an LOG standard or an LN, it's a log base 5. Calculator cannot do this for me, at least not straightforwardly. So I am going to say let minus log base 5 of 125, let that be equal to something. Let it be equal to y. Now what's bothering me here is that, well, bothering is a big word, there's a negative here. And for the first time, there's something in front of a log. What should I do with it? Well, I suggest that we do not deal with it. I suggest that we bring it to the other side. All right? So let's have a standard thing here that we are used to, which is log base A of something equals to our right-hand side. For that, move the minus to the other side. And then I am in a familiar situation. This to the power of that is equal to the inside of the log. So 5 to the minus y is equal to 125. This is where we stand at this moment. 5 to the minus y is 125. We are going to be successful if we can write, this is a little not very clear, my apologies, minus y is the power of 5. We will be successful if we know how to write 125 as a power of 5. So 5 to what power? So 5 to the 1 is 5, 5 to the 2 is 25, 5 to the 3 is 125. We've been successful writing them the same base, 5 and 5, so it follows that the exponents must be the same. So minus y must be 3, so clearly y has to be minus 3. Quick check. Well, actually before the check, perhaps write down the answer. Y was basically what I called the original question. So, conclusion, minus the log of 125 base 5 is equal to y, which is minus 3. Quick check. Quick check. Minus log of base 5 125 is equal to minus 3. Let us check this. Minus on the left, minus on the right. Cancel the minuses. So that's the same as log 125 base 5 equals to positive 3. Raise this to the other side and make it equal to the inside of the log. So 5 to the 3 is 125. Right or wrong? Correct? Check. And that actually concludes our introduction to logarithms. Next video, we'll take a look at the log function. What is its graph, or the different ways to express the graph, and we'll talk about domain and things like that. Hopefully this was not too overwhelming. I will see you in the next one. Take care of yourself.